Introduction to Spectroscopy. I am Dr. V.T. Joy, Assistant Professor and Head of the Department of Chemistry, Christ College Autonomous, Chinchalagoda. The word spectroscopy derives from two words. Spectrum from Latin word spectron, and it has a meaning ghost, spirit or image, and scopy from Greek word scopin, and it has a meaning to view, examination, evaluation, looking to the world, etc. So how we can define the term spectrum? A spectrum is a range of waves such as light waves or radio waves within a particular frequencies. Example, a band of colors produced comprising red, orange, yellow, green, blue, indigo and violet when sunlight is passed through a prism or through a drop of water. So here is an example for a spectrum, a rainbow. Sunlight split into 7 colors. And this is another example for a spectrum, white light coming out of a prism. Properties of electromagnetic radiation. An electromagnetic wave is a self-propagating transverse wave consisting of oscillating electric and magnetic fields. An electric field that oscillates as a function of time will produce a magnetic field and vice versa. The electromagnetic radiation transports energy from one point to another point. This radiation propagates through space at approximately 300,000 kilometers per second. As the radiation propagates at a given frequency, it has an associated wavelength, that is, the distance between successive crests or successive troughs. An electromagnetic wave is characterized by several fundamental properties, including its velocity, amplitude, frequency, phase angle, polarization, direction of propagation, etc. For example, the amplitude of an oscillating electric field at any point of time along a propagating wave is given by the expression AT is equal to AE into sine 2 pi nu t plus phi. Here AT is the amplitude of the wave at any time t and A is the maximum amplitude. Nu is the frequency and phi is the phase angle, which accounts for the fact that AT need not have a value 0 at time t equal to 0. The velocity of the light is given by the expression c is equal to nu lambda, where nu is its frequency and lambda is the wavelength. The electromagnetic radiation can be described in terms of a stream of massless particles called photons, each traveling in a wave-like pattern at the speed of light. Each photon contains a certain amount of energy. The energy of the photon is given by the expression E is equal to h nu, and nu may be replaced by c by lambda. Here h is the Planck's constant. Another useful unit in spectroscopy is the wave number, which is the reciprocal of wavelength, and it is represented by the symbol nu bar. Wave numbers are frequently used to characterize infrared radiation, with the units given in centimeter inverse. Since all electromagnetic radiation travels at the same speed, the number of waves passing a given point in space in a given unit of time varies with the wavelength. In this figure, it can be seen that in the case of first radiation, 4 waves are produced in 1 second, 8 waves in the case of second radiation, and 16 in the case of third radiation. So, 4 waves pass through a given point in the case of first radiation, 8 in the case of second radiation, and 16 in the case of third radiation. The electric and magnetic fields oscillate perpendicular to each other, and their oscillations are also perpendicular to the direction of waves propagation. In ordinary light, the electromagnetic waves oscillate in all possible planes. If that light travels through a Polaroid or an equiprism, then the emerging light will have oscillations only in one plane. Such a light is called plane polarized light. This animation shows an example of a plane polarized electromagnetic radiation consisting of a single oscillating electric field and single oscillating magnetic field. So a molecule at this point is subjected to periodically varying electric field of the incident radiation. The electric field increase reaches a maximum, decrease 0, then goes negative, again 0, and the whole cycle repeats. In some forms of spectroscopy, like rotation spectroscopy, it is the oscillating electric field of the electromagnetic radiation that interacts with the matter. And in some other forms of spectroscopy, like nuclear magnetic resonance, it is the oscillating magnetic field that interacts with the molecules. The electromagnetic spectrum is generally divided into 7 regions in order of decreasing wavelength and increasing energy and frequency. So the radiation having the longest wavelength is radio waves, followed by microwave, infrared, visible, ultraviolet, X-rays and gamma rays. Gamma rays have the highest energy, and it can be seen that radio waves can have wavelengths up to 100 kilometers. Here is a comparison of wavelengths of different radiations with the size of real objects. Here radio waves has size of buildings, microwave has size of water bottles, infrared has size of pinhead, visible and ultraviolet has the size of molecules, X-rays have the size of atoms, and gamma rays have the size of atomic nuclei. Even though the electromagnetic spectrum spans over 15 orders of magnitude of photon energy, the visible part of that range comprises much less than 1 order of magnitude. For reasons of convenience, different units are used for expressing the energy of the radiations belonging to different parts of the spectrum. Visible and ultraviolet region of the electromagnetic radiation is usually expressed in terms of wavelength in the units of nanometer, and visible radiation has a range of 400 to 700 nanometers, and ultraviolet has a range of 1 to 400. If visible radiation is expressed in terms of wavelength in the units of centimeters, then we get very small numbers, and if visible radiation is expressed in terms of frequency in hertz, then we get very large numbers. So it is most convenient to express the energy of visible radiation in terms of wavelength in the units of nanometers. Spectroscopy deals with measuring and interpreting spectra that arise from the interaction of electromagnetic radiation with the matter to obtain information on the structure and properties of matter. Here a molecule is subjected to periodically varying electric field of the incident radiation. This induces a dipole in the molecule, and this dipole oscillates at the same frequency of the incident radiation. This gives rise to a phenomenon called scattering. Here sunlight reaches Earth and interacts with materials present on the Earth's surface. A part of the radiation is absorbed by the materials and part of it is emitted to the space as heat radiation or infrared radiation. These radiations are absorbed by some gases present in the atmosphere. Examples for these gases include carbon dioxide, methane, water vapor, etc. On absorbing these radiations, these molecules get excited to higher vibration levels. Soon they return to ground vibration levels, and excess energy is emitted in the form of heat radiation in all directions uniformly. A part of these emitted radiations comes back into Earth. This phenomenon, known as greenhouse effect, helps Earth to have a warm atmosphere. Without greenhouse effect, it will be very cold in the night time and very hot in the daytime, and life would be impossible on this planet. But nowadays, we are concerned about enhanced greenhouse effect. It arises due to increase in the levels of carbon dioxide in the atmosphere. Before Industrial Revolution, the level of CO2 in the atmosphere was 280 ppm, and nowadays the level has increased to about 415 ppm. This causes an increase in the temperature of the planet, the so-called global warming. This causes severe climate changes and has many detrimental effects like floods, droughts, rise in sea levels, melting of glaciers, hurricanes, etc. Electromagnetic radiations in our daily life. If you have used a microwave oven today, then you have used microwave radiation. If you have used a cell phone today, again you have used microwave radiation. If any of your relatives took a MRI scan, then they have used radio waves. If the dentist took an X-ray at your last visit, he has used X-rays. If you have heard the term global warming today, it results from the interaction of greenhouse gases with infrared radiation. If you have heard these days about thermal scanning used for COVID-19 detection, it works on the principle of emission of infrared radiation radiated from a person suffering from fever. And if you have used a TV remote control today, then you have used infrared radiation. It is hard to imagine a world without colors simply because they are all around us. Have you ever wondered where do these colors come from? When light heats matter, one or more of the following phenomena happens. It is transmitted, absorbed, refracted, reflected, scattered, etc. Here, the light is reflected and the surface appears white, and here all the light is absorbed with the material and the surface looks black. Here all the light is transmitted. So first let us see what is transmission. If the incoming light energy is much lower or much higher than that required for electrons for excitation, then the light source will pass through the material unchanged. This way the matter will look transparent to the human eye, such as in the case of glass. Absorption. It occurs when there is no reflection and the incoming light source frequency is same as or very close to the absorption frequency of the electrons in the given material. The electrons thus absorb most of the incoming energy with little or no reflection. Here all these colors are absorbed by this material and it looks black. Third, reflection. The change in direction or bouncing back of a wave when it strikes a surface is called reflection. The surface is smooth and shiny like surface of glass or surface of a polished metal. The light will reflect at the same angle as it hit the surface. The light energy sent out of the material has the same frequency as the original light coming in. Color of a material. The color of an object or material is mostly determined by the wavelengths it absorbs and those it reflects. An object has the color of wavelengths it reflects. A material that reflects all wavelengths of visible light appears white. A material that absorbs all wavelengths of visible light appears black. A surface that absorbs all wavelengths except green, which it reflects, looks green as shown below. So this green leaf, it absorbs all colors of visible light except green, which it reflects. So to an observer, the leaf appears green. Refraction occurs when light travels at an angle into a substance with a different refractive index. The change in direction is caused by a change in speed. For example, when light travels from air into water, it slows down, causing it to continue to travel at a different angle or direction. The refraction in a prism causes white light to separate into its constituent wavelengths. The different colors correspond to light with different wavelengths. Here the sun is already below the horizon. Atmospheric refraction makes the sun visible even when it is just below the horizon. Advanced sunrise and delayed sunset. The sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction. This figure shows the actual and apparent positions of the sun with respect to the horizon. So here the actual position of the sun is below the horizon. Sunlight travels in straight lines, but when it reaches the S atmosphere, it bends, and to the observer, the sun appears at this position. The apparent position of the sun is here. It is above the horizon, and it is due to refraction. Fifth is scattering. Scattering occurs when a particle of light is fully absorbed and then emitted in all directions, while in reflection a wave is simply reflected off the surface without interacting. Scattering of light gives rise to many spectacular phenomena such as Tyndall effect and red hues of sunrise and sunshine. So in this experiment, a laser light is passed through a sugar solution and a milk solution. Path of light is visible in the case of milk and not in sugar solution. This is due to scattering of light by colloidal particles present in milk. Such colloidal particles are not present in the sugar solution. Sugar molecules and water molecules being extremely small, scattering of light by these molecules is very weak. Why clouds are white and sky is blue? The sky is blue due to Rayleigh scattering of the sunlight mainly by the molecules of the atmospheric gases. For Rayleigh scattering, the size of the particles has to be much smaller than the wavelength of the light, and indeed the air molecules are. In that case, the shorter wavelengths are much more scattered than longer wavelengths. So blue is more scattered compared to red, and the sky appears blue. But the droplets in clouds are bigger than wavelengths of sunlight. Therefore, a different kind of scattering takes place, and it is known as me-scattering. And this happens to all wavelengths in equal amounts. Mixing of colors. The primary colors of light are red, green, and blue. Mixing these colors in different proportions can make all colors of light we see. This is how a TV and a computer screen works. When colored lights are mixed together, it is called additive mixing. Red, green, and blue are primary colors for additive mixing. If all these colors of light are shown to a screen at the same time, you will see white. And if a green light and red light are mixed, then we will see yellow light. This is different when you are mixing paints. It is called subtractive mixing. Each color of paint is absorbing certain colors and reflecting others. When you mix magenta and yellow, you get a red color. Absorption and emission spectroscopy. Absorption spectroscopy refers to spectroscopy techniques that measure the absorption radiation as a function of frequency or wavelength due to its interaction with a sample. The intensity of the absorption varies as a function of frequency. In emission spectroscopy, atoms or molecules are excited to higher energy levels by light, heat, electricity, etc. Excited species decay to lower levels by emitting radiation, and it is known as emission or luminescence. For atoms excited by high temperature energy source, this light emission is commonly called atomic or optical emission, and the technique is known as atomic emission spectroscopy. And for atoms excited with light, it is called atomic fluorescence, and the technique is known as atomic fluorescence spectroscopy. Atomic and molecular spectra can provide detailed information about the structure, geometries, bond lengths, bond angles, torsion angles, molecular symmetry, etc. Here is a simplified energy level diagram showing absorption and emission of a photon by an atom or a molecule. In absorption spectroscopy, when a photon of energy h nu strikes the atom or molecule, absorption may occur and atom or molecule get excited to a higher energy state. In emission spectroscopy, an atom or molecule originally in an excited state may emit a photon and return to the ground state. Bohr condition for absorption of light. When a light falls on a material, then Bohr condition for absorption light is that the atom or the molecule absorbs only that radiation which has frequency given by the expression E2 minus E1 by h. A spectrometer. A spectrometer is an apparatus that measures the intensity of the light entering a sample solution and the intensity of light going out of the sample solution. The ratio of the two intensities can be expressed as transmittance T. So transmittance T is given by IT by I0. Here I0 is the intensity of the incident light and IT is the intensity of transmitted light. The Beer-Lambert law. The Beer-Lambert law states that the quantity of light absorbed by a substance dissolved in a fully transmitting solvent is directly proportional to concentration of the substance and path length of the light through the solution. So A is proportional to C and L. So we may write A is equal to a constant epsilon CL. Here A is the absorbance, epsilon is called molar absorption coefficient, and C is the molar concentration, and L is the optical path length. When path length of the cell is 1 cm and concentration is 1 mole per liter, then absorbance is equal to epsilon. So we may define molar absorption coefficient as the absorbance of a solution of 1 molar concentration and path length 1 cm. So this animation shows a light having intensity I0 hitting the sample, and a part of it is absorbed by this sample, and the outgoing radiation is diminishing in intensity. We may define transmittance as I2 by I0, and absorbance may be defined as log of 1 by T, or we may write negative logarithm of 1 by T. A completely transparent substance will have IT equal to 0 and its percentage transmittance will be 100. Similarly, a substance which allows no radiation of a particular wavelength to pass through it will have IT equal to 0 and the corresponding percentage transmittance will be 0. So here is a comparison of absorbance values to the transmitted values. When absorbance 0, transmittance is 100%. When it is 1, then transmittance is 10. When absorbance is 2, then transmittance is 1, and so on. How the value changes as path length or concentration is increased. Transmittance. Transmittance decreases exponentially and absorbance increases linearly. Now range of transmittance and absorbance. Transmittance values range from 0 to 1 and absorbance values range from 0 and upwards. Here is a plot of transmittance versus concentration, and we can see that transmittance decreases exponentially with increase in the concentration. An application of Beer-Lambert law. Using Beer-Lambert law, we can find the concentration of a substance using the expression A is equal to epsilon C into N. Here epsilon is a constant for a given sample and L is the path length of the cell, which is constant for a given cell. So A is directly proportional to C. We first make a series of solutions of known concentrations, measure their absorbances using a colorimeter. Then plot a graph of absorbance versus concentrations, we get a straight line. Then we measure the absorbance of the solution of unknown concentration and we extrapolate to the graph and we can find the unknown concentration of the substance. A monochromator is an essential part of a spectrometer. In order to gain maximum information, the interaction or emission light should be measured as a function of wavelength, and a common feature of all optical spectrometers is therefore a mechanism for wavelength selection. The device used for this purpose is called a monochromator. A monochromator consists of three essential parts: an entrance slit, a dispersion device such as a prism or a grating, and an exit slit. White light from a source passes through the entrance slit and is split into constituent colors by the prism, but only a light beam having a particular frequency or color can pass through the exit slit. Here it is the green light passing through the exit slit. By rotating this prism, we can select light of any frequency or color. An absorption spectrometer. An absorption spectrometer is a device to measure the absorption of electromagnetic radiation from a sample. Here, from white light, we select light of a particular frequency using a monochromator, and it is passed through the sample, and the intensity of the transmitted light is measured with a detector. The intensity measured with only pure solvent may be taken as I0, and with the sample solution it may be taken as IT. The ratio of IT to I0 gives transmittance, and the transmittance values may be plotted against wavelengths to get a spectrum. Different substances absorb different wavelengths of light. Absorbances plotted against wavelength gives absorption spectrum, and a transmittance plotted against wavelength gives a transmittance spectrum. The wavelength of maximum absorption, lambda max, of a substance is one of the characteristic properties of that material. So here absorbance is plotted against wavelength, and at this wavelength absorbance has the maximum wavelength. But here transmittance is plotted against the wavelength, and at lambda max the transmittance has the lowest value. An emission spectrometer. An emission spectrometer is a device to measure the emission, which may be fluorescence, phosphorescence, or electroluminescence, of electromagnetic radiation from a sample. To obtain an emission spectrum, the excitation monochromator is set to some wavelength known to excite the molecule, and emission monochromator is scanned through different wavelengths. Molecular energies. A molecule consists of a group of atoms. Electrons in an atom have some discrete energy levels. Molecule has translational, rotational, and vibrational motions. Hence, the molecule has following energies. Translation energy. It is due to the motion of center of mass of the molecule. Electronic energy. It is due to the motion of electrons in various energy levels in the molecule. Vibration energy. It is due to the vibration motion of the atoms in molecules about its center of mean position. And rotation energy. It is due to the rotation motion of the molecules about its center of mass. Hence, total energy of the molecule is sum of translational, electronic, vibrational, and rotation energies. The translation energy is negligible and it is not quantized. So we may ignore translation energy, and the total energy of the molecule is given by sum of electronic, vibrational, and rotational energies. Molecular energy levels. While the separation between electronic energy states is of the order of 8,360 cm inverse to 836,000 cm inverse, the separation between vibrational energy states is of the order of 8,000 to 100 cm inverse. The separation between the rotational energy states is of the order of 1 to 100 centimeter inverse. Rotational energy is the energy associated with a molecule when it is rotating about an axis passing through center of gravity. Rotation energy is quantized. This leads to discrete energy levels. The difference between successive rotation levels is of the order of 0.01 to 1 kilojoules per mole. The absorption radiation in the microwave region causes transitions between the rotation levels. Vibration energy is the energy possessed by molecular vibration motion in which there is periodic displacement of the atoms from their equilibrium positions. The difference between the successive vibration levels is of the order of 1 to 100 kilojoules per mole. The absorption radiation in the infrared region causes transitions between the vibration levels. Electronic energy is the energy associated with distribution electrons in molecules in various molecular energy levels. The difference between successive electronic levels are of the order of 100 to 10,000 kilojoules per mole. The absorption of the electromagnetic radiation in the ultraviolet, visible or near infrared region cause transitions between these levels. Why nitrobenzene is pale yellow colored? Nitro group in nitrobenzene is a chromophore. It absorbs 400 to 450 nanometer region of the visible spectrum and transmits all other colors. The transmitted light will have complementary color of the absorbed region and it is yellow. This yellow light consists of all colors of visible spectrum except blue. This can be proved by passing the transmitted light through a prism. The spectrum coming out of prism will consist of all colors except blue. So here light from nitrobenzene, transmitted from nitrobenzene is passed through prism and we see all colors except blue. Fluorescence is a property of some atoms and molecules to absorb light at a particular wavelength and to subsequently emit light of longer wavelength after a brief interval. In this session, we will discuss the fluorescence from a compound known as fluorescent. The structure of this molecule is given here. And this is a solution of fluorescent in water. We can see two different colors, a green color and a yellow color. Yellow color is the color of the transmitted light and green color is the color of the emitted light. Let us examine origin of these two colors in detail. To know which color of the visible spectrum the sample absorbs, we first record a UV visible spectrum of this compound and we get a graph like this. We get a band centered around 450 nanometer. This 450 nanometer is the wavelength of blue radiation. That means fluorescent sample absorbs blue part of the radiation and transmits all other colors. So the transmitted light will have a color complementary to that of blue and it is yellow. That is why the transmitted light has a yellow color. Now what happens after absorbing this blue radiation? The molecule gets excited from the ground electron state to various vibration levels of the first excited electron states. From higher vibration levels, it comes to the lowest vibration level by non-radiative transitions. From the lowest vibration level of the first excited electron state, it undergoes a radiative transition to various vibration levels of the ground electron state and emit X energy in the form of light, and this light has green color. And to know which color it is emitted, we record a emission spectrum and we get a spectrum like this and we get a band around 520 and this 520 is the color of green light. Thanks for watching.